so that's the trachea. Which of the zones that we talked about earlier would the trachea be included in? Conducting or respiratory?
Conducting?
It's in the conducting zone, right? It's just delivering air. There's no gas exchange that can take place there. Until you get down to, oh, here's a picture of the cross-section just like we drew. There's our ciliated epithelium. There's the hyaline cartilage ring, except on the posterior side to accommodate food moving through the esophagus. Now, as I mentioned, there are 23 orders of division that the respiratory system undergoes. So it starts in the trachea, which then divides. And then those structures divide too. And then they do, and they do, and they do. 23 times. And we refer to the appearance of those airways as the bronchial or respiratory tree. Sometimes this throws people. The respiratory tree is not a particular thing. It's the name given to the appearance of this branching pattern of the respiratory system. And again, every time these split, every time they branch and divide, they're getting a little smaller, and the structure you create is delivering air to a more specific part of the respiratory system. So let me explain what I mean. You've got the trachea, right? Your main airway. It delivers air to the entire respiratory system. And then you get down to the level of about mid-sternum, and you have your first division, and you have the primary bronchi, each one delivering air to one lung, right? Trachea for the whole respiratory system, primary bronchi for a lung. So each time you divide, it's a little smaller, and it's delivering air to a more specific area. So those are the primary bronchi that I mentioned there. Sometimes called main stem, but primary bronchi is the way we're going to go in here. So each primary bronchus is responsible for delivering air to each lung. What do the primary bronchi then do? They also divide. Here's our trachea right here, and bringing the air down through our throat, about the level of mid-sternum. It divides into the primary bronchi. Each one delivers air to each lung. The primary bronchi then divide as well. What do you suppose we get when the primary bronchi divide?
Secondary.
The secondary bronchi, exactly. Like I said, after each division, you have air being delivered to a more and more specific part of the respiratory system. So, trachea, whole respiratory system. Primary bronchi, individual lung. Secondary bronchi delivers air to an individual lobe of the lung. So if you look at a lung, which we will, it has these divisions, these deep cracks that go down through them called fissures. The fissures, again, they're divisions. They divide the lungs into lobes. Air is supplied to a lobe by a secondary bronchus. So do you see what I mean by more and more specific parts? The whole thing, each lung, each lobe of each lung. There are even smaller little divisions after that called segments. We won't really get into that because it's not visually apparent. So 23 orders of division, each time bringing things to a more specific part. If you look at the secondary bronchi that I drew up there, what do you notice? Comparing right and left. One, two. 2, 3, right? There's more on the right side than on the left. Here's a right lung. How many lobes does it have?
3.
3. Again, 1 supplied by each of the secondary bronchi. But the left lung looks more like this, with only 1 fissure and 2 lobes. So on the left, we have 2 secondary bronchi. Why does the left lung only have 2 lobes?
Does it have anything to do with the placement of the heart?
It has everything to do with the placement of the heart. So remember when we talked about the heart in the last unit, it's roughly in the middle, but not exactly in the middle. It's over to the left a little bit, right? Taking up some of the space that would otherwise be dedicated to the left lung, making the left lung smaller and only divided into 2 lobes. The right lung, on the other hand, has more room, so it's a little larger, and it gets divided into 3 lobes. So again, the respiratory structures continue dividing, and the secondary bronchi divide and give us the tertiary bronchi. And after that, we stop numbering them. We don't get to quaternary and whatever you call 5th order. I don't even know the word for that. Okay, but it goes trachea, primary bronchi, secondary bronchi, tertiary bronchi, and then they just become bronchioles for many, many divisions without more specific names. 23 orders of division, right? So far we've done 1, 2, 3. To get to bronchioles is number 4. We still have 19 more orders of division left, and of those, 16 of the remaining 19 are just called bronchioles. Okay, so they range from small but large enough to see with the naked eye, all the way down to microscopic, as they continue dividing, getting smaller and smaller each time. Here's a good picture. So this is a cast of the respiratory passageways, and you can see the structures we just talked about. What would this be? The trachea. That divides to give you the primary bronchi supplying air to each lung. The primary bronchi then divide to give you the secondary bronchi, supplying air to each lobe of each lung. The secondary bronchi then divide, giving us the tertiary bronchi. We didn't really, like I said, I didn't really get into it too much. They supply a region of the lung known as a segment. I don't really get into segments because they're not visually apparent when looking at a real lung. Now in this one they've color-coded it, so each color, orange, pink, blue, red, yellow, green, white, represents a segment. But all that really is an area of the lung supplied by a tertiary bronchus. And you can see how, if we flip it upside down, it's a lot like the way a tree branches, right? With the trunk being the trachea, coming up and then branching into all of these. Obviously, we're looking at a tree in the winter or something because there's no leaves, but the analogy holds up. So these structures remain bronchioles until you get down to this microscopic level here, where we finally give them a different name and call them terminal bronchioles. So we're again 16 orders of division later, but we finally call them something else. Terminal bronchioles. Terminal bronchioles, it says less than 0.5 millimeter in diameter. So you're basically in the microscopic range here, okay? Maybe you can see with magnifying glass, but that would be it. What does this word terminal mean?
The end?
Yeah, it means the end, because these are the end of the conducting zone, okay? So this whole time, from our bronchi all through all the bronchioles until we get to the terminal bronchioles, no gas exchange taking place, right? Well, here in the terminal bronchioles, it is the end of the conducting zone, meaning the next structure we get to will be the beginning of what's the other one besides conducting zone?
Respiratory.
Respiratory zone.
I had to look.
I was like, what am I looking
And the first structures in the respiratory zone, see they're making it easy on you this time. Terminal, the end of the conducting zone.
I'm not used
The
to
next, yeah, I know, it throws you off, right? The next one, the beginning of the respiratory zone, they're called respiratory bronchioles. So, sometimes they make it easy. And as the name implies, you now are capable of undergoing gas exchange. Here, beginning with the respiratory bronchioles. This is not the last structure in line, but we still have some gas exchange that takes place. They are small enough that we can have exchange of oxygen and carbon dioxide between the respiratory bronchioles and the bloodstream. The little air sacs of the lungs are called alveoli. Anybody know what this word alveoli means? In Greek or Latin or whatever it was? It means grapes. So these little air sacs are in clusters, we call alveolar sacs, that looks like a cluster of grapes. Like this. Okay. So each one, the singular version of that, by the way, is, they're writing alveoli because they're labeling more than one. The singular version of that is alveolus. But the alveoli are organized in these clusters. So here you see a terminal bronchiole representing the end of the conducting zone. It divides to give us respiratory bronchioles, the beginning of the respiratory zone. Eventually they feed into the alveolar duct and then the alveoli themselves. Obviously that's a drawing. Here's what it looks like under the microscope. We'll take a look at lung tissue in lab under the microscope. All of these little compartments, those are alveoli. And here you're seeing the tiny little airways that supply them. A respiratory bronchiole, what would that make this then, by the way? If you see the respiratory bronchiole branching off of it, this would be a terminal bronchiole, right? So there's a respiratory bronchiole and then the alveolar ducts leading into all of these little air sacs. The majority of the respiratory zone is alveoli. Okay, so yes, some gas exchange can take place at the respiratory bronchioles, at the alveolar ducts, but the majority of it is happening in the alveoli. It represents the largest part of what we call the respiratory membrane. So when we talk about the respiratory membrane, we're talking about the total surface area where gas exchange can take place, the majority of which is alveoli. And it says here, those alveoli make up the majority of the volume of your lungs. I think of this lung tissue, the airways and the alveoli, in a lot of the same ways that I think of blood vessels, right? So you've got, like take for example the systemic circuit. It starts with one big artery, the aorta, supplying the entire systemic circuit. As that moves out into your body, it branches and gets smaller and smaller and smaller until ultimately you get all the way down to capillaries. The capillaries don't seem that important because they're so small, but that's actually where all of the important activity is taking place, right? That's where tissue and blood interact, not at the arteries. Same deal here in the lungs. You've got big, large passageways like the trachea and the primary bronchi, but most of the action is actually happening all the way down at the smallest microscopic level, here in the alveoli themselves, because this is where exchange takes place. This is the purpose of all of the other structures. They're saying about 300 million alveoli per lung. I've read somewhere that the total surface area of the respiratory membrane is something like the area of a tennis court per lung, is the total surface area that we're talking about. So it's quite large. There's another statistic, I think it's in here on one of these slides. See it? Where it compares the surface area of the respiratory membrane to, I forget what they said, I want to say it's something like 10 times the surface area of your skin or something like that, which is kind of interesting to think about. So here at the respiratory membrane, do you guys remember what tissue type those alveoli should be made of histologically? Simple squamous. Single layers of cells that are really, really thin. How thin? Well, about half a micrometer. And I don't have a good analogy to demonstrate how thin half a micrometer is, but it's pretty thin. Okay? And of course, the efficiency of gas exchange relies on that very thin barrier, right? What do you suppose would happen if something were to cause that barrier to thicken?
Inefficient.
Yeah, it would be inefficient. It would slow down the transport because the greater distance, the greater amount of cell that stuff has to go through, the slower it's going to be, right? So the thinness of the respiratory membrane is important. So the alveoli themselves are composed of this simple squamous epithelium. We call those cells type 1 alveolar cells, but contained within them are also type 2 alveolar cells. Type 2 alveolar cells are secretory cells. That means they secrete something. And what they do is secrete this stuff called surfactant. Anybody know what surfactant is? It relates to a property of water we call surface tension. Surface tension is a result of the water molecules' attraction to each other. Water molecules have polarity, right? So the oxygen end has a slightly negative charge, the hydrogen end has a slightly positive charge. What do opposite charges do? Attract, right? So the water molecules stick together, creating surface tension. And that's handy for things like water strider bugs because they can walk on the surface of the water as the attractive force of the water molecules is supporting the weight on top of it. But in us, especially in the lungs, surface tension is our enemy. Because if you imagine those little alveoli, those little air sacs, they're moist, right? This internal membrane, it has water molecules all around it. These will be water molecules. And if water molecules are attracted to each other, as we just said they are, what would that do to the alveoli as all of these want to come closer together? Not necessarily dry it out. If all of these water molecules are trying to come together, that would collapse the alveolus, right? And by extension, make it harder to inflate when we want to breathe in because those water molecules' attraction is resisting that. And so it would make it harder to breathe. The lungs would tend to collapse inward. So surface tension is bad in our alveoli. Surfactant is stuff that eliminates surface tension, and therefore makes it easier to inflate the lungs. I'm sure several of you have probably heard of this before. One of the major problems that can occur if a baby is born too prematurely is respiratory distress. Right? They have trouble breathing. They're born too prematurely. One of the reasons why is that these surfactant secreting cells are not ready yet. They've not yet begun producing surfactant. And so if the baby's born early, they're struggling against the surface tension inside their lungs every time they need to breathe. It makes it very difficult because they're not eliminating that surface tension yet. So that's produced by type 2 alveolar cells. Here's a depiction of that. So here's one of the air sacs. All of these are type 1 alveolar cells, just simple squamous epithelium like we talked about, allowing easy exchange back and forth with these little capillaries. These green ones are the type 2. They produce surfactant for reasons we just discussed. And these little blue guys here are alveolar macrophages. Alveolar macrophages are also sometimes called dust cells. What do macrophages do? They eat. They are big eaters, right? And in the case of the lungs, it could be that they're eating, potentially disease-causing organisms, as they do in several other tissues. But look at their name. They're also called dust cells, right? We have this whole filtration mechanism as air is making it down into the lungs. But is it possible some of those tiny little particulates actually make it into the lungs? Yeah, and so macrophages help with that too. And check this out. It says alveolar macrophages keep the surfaces sterile, right? We know that, okay? 2 million dead macrophages are carried out of the throat every hour by that mucus elevator there in your conducting zone. Isn't that gross?
Yeah, I saw that.
Yeah.
I was like,
But you know what they say, better out than in, right? So. Alright, some more anatomy on the lungs. Again, we're going to cover that more in lab. Let's move on to talking about the pleura. The pleura is the serous membrane that covers the lungs, and like all serous membranes, it's double layered. So what do we call the innermost layer?
visceral,
The visceral pleura, and the outer layer then would be
parietal.
the parietal pleura. Good. And of course, those two layers, what did I do? Those two layers are actually continuous with each other, so you can see that in the picture here. Here's the visceral layer right on top of the lung. To create the outer layer, it just reflects back on itself there and becomes continuous with the wall of the thoracic cavity with a small space in between it. And it's shown pretty small here, but in reality it's probably even a little smaller than that, the space between them. And that pleural cavity, or pleural space, is filled with a fluid, which again helps to reduce friction and that kind of thing. So like all serous membranes, it's going to be involved in allowing movement of this organ without friction, because these layers are very smooth, they have that lubricating fluid in between them, you get nice frictionless movement. But the pleura are also really important in the mechanics of ventilation, what causes the lungs to inflate, for example. The pleura are tied in with that. You guys remember what I said was the main muscle that drives ventilation?
Diaphragm.
The diaphragm, right. So if our lungs look like this, right lung, it's the left lung. We know they're covered in this pleura. You've got the visceral layer, and then you've got the parietal layer, which is attaching to the rib cage and other parts of the body wall. But the parietal pleura down here at the bottom is also attached to the diaphragm muscle. So that when the diaphragm muscle pulls down, it's pulling down on the pleura. Okay? And we'll get to how that works here in just a little bit, but since we're talking about the pleura, I wanted to point that out. The act of breathing, pulmonary ventilation, has two main phases, inspiration and expiration. Inspiration meaning to breathe in, and expiration meaning to breathe out. Pretty intuitive. The reason why we want to talk about that and establish that before we move forward is that those two phases are driven by different mechanisms, and it will be worth noting. The next few slides we're going to be talking about pressure. And the reason why is because movement of air is driven by differences in pressure in all cases. Even the wind outside is driven because there are differences in pressure across geologic spaces, right? You've got a high pressure system over here and a low pressure system over here. Which direction will the wind blow?
Towards the low pressure.
Yeah, from high to low, okay? And it works the same way when we're talking about our breathing. Air is still going to move from areas of higher pressure to lower pressure. The way that you create ventilation is by changing the pressure in your lungs to be either higher or lower than the air around you. Like a balloon, for example, right? You blow up a balloon by forcing air in. Higher pressure pushes it into the balloon. If you then, you're holding the balloon, if you take your fingers off of it, there's greater pressure inside the balloon than in the room around you, so the air moves out, right? And we're using the same ideas here in our own ventilation. Just like the wind, just like a balloon being blown up, it works the same way. So first, they're talking here about atmospheric pressure. This just means the air pressure around you. And it's a result of, weather systems change it, but by and large it's a result of the atmosphere pushing down on you. So where is there lower pressure?
Higher elevation.
Higher elevations, right? In a couple weeks, me and the family were going camping over at Medicine Lodge Lake. Have you guys ever been there?
Heard of it.
Yeah, it's supposed to be really nice. Anyway, it's like 9,300 feet, right? So a lot lower pressure up there. It's almost into the wilderness area. So you take 14 and turn off on a forest road and go like 24 miles. I think it's maybe 10 miles north of West Hensleep Lake. It's in that area. Anyhow, higher elevations, lower pressure, basically because there's less atmosphere pushing down on you. You go down to lower pressure or lower elevations, greater pressure, because now there's a thicker atmosphere pushing down on top of you. This is our average, 760 millimeters of mercury. So again, we're measuring pressure in that strange unit. Now again, this will vary because we know elevation changes things, and they're mentioning right there that that's at sea level. Also, weather patterns can change this slightly. Here in Sheridan, given our elevation, we're at about 88% of the sea level elevation. So if sea level is 760 millimeters of mercury, and we're only about 88% of that, average atmospheric pressure here is about 669 millimeters of mercury. Okay? So that's our average atmospheric pressure. When we talk about respiratory pressures, what we mean is the difference between the atmospheric pressure around us and the pressure inside our lungs. On the next slide, I'll call it intrapulmonary pressure. If the pressure in your lungs is less than the pressure around you, that's a negative respiratory